Today we're going to review the VSEPR theory. VSEPR stands for valence shell electron pair repulsion. And in the VSEPR theory, we are determining the different shapes and geometries that these different molecules will take on as a result of their repulsion around the electron pairs repelling around the central atom of any molecule. So we'll start off with AB notation, just the AB. In the AB notation, here's your central atom. You then bond one bond to that central atom, so now you have an AB notation. The AB notation has an angle, not really, you can't really determine the angle other than it looks like a 90 degree or 180 degree angle. The reason why you can't really say there's much of an angle because in order for you to be able to determine angle, you need 3 points. And I guess you can say that there's a point right here. However, we're looking at the bonded atoms in the central atom. Now we're going to take another bond. This is AB2, AB2. In AB2, I'm going to stick it right on the opposite end, making now a linear shape with an angle measurement of 180 degrees, 180. So this shape is oftentimes occurs with your incomplete octets, like an atom like beryllium. Now we get to another incomplete octet. However, it could also be double bonded to one of the atoms for this shape to take on. And so I'm going to rebond these two bonds downward in order to utilize all the spacing around the central atom, giving me a shape that's called trigonal planar. Notice this all the bonds are on a single plane, and it makes a triangular shape right here. The angle measurement for this triangular shape is 120 degrees. Now we're going to add the next bond. The next bond is AB4. This is AB3 right here. AB4 is when you add another bond. In adding this extra bond, these bonds that were on the trigonal planar move downward. And literally you should be rebonding them because they'll go back to their original shape if you don't rebond them at an angle. Okay, so if you rebond them, you'll notice it makes this triangular shape here. And then of course you put the fourth bond on top and you've made what is called a tetrahedral shape. Now the way you check your tetrahedral shape is you rotate it around, and if it doesn't have that head sticking up straight up, then you have to readjust. Again, readjustment, even if it's slight, to make that head stick to the top. And it's straight up. Okay. And if you do it on all bonds, you'll notice that it will create your perfect tetrahedron shape. And it does. If you flip it all the way around, you'll see it straight up. Okay. The angle for this is 109.5 degrees all the way around, so equally spacing those electron pairs as far apart from each other as possible. A very popular shape because you're looking at following what is called the octet rule with 4 bonds. 4 times 2 gives you the 8 electron pairs around the central atom. Now we get to the next shape. The next shape is your expanded octet. In the expanded octet, I'm going to revert back to the trigonal planar. So I'm going to start off by making my bonds into a trigonal planar. Once I do that, and you'll notice all the bonds are on a single plane and it's triangular shape. Then I put my next 2 bonds, one on top of the trigonal planar and the opposite one on the bottom. And you'll notice the shape that comes out of this is called a trigonal bipyramidal. And look at the pyramid. You'll see a pyramid on the top, and you'll also see a pyramid on the bottom. Thus, it's called trigonal bipyramidal. Okay? The 2 angles that are in this shape are 120 degrees, where it's trigonal planar, and then, of course, 90 degrees right here where it's perpendicular to the trigonal planar, whether it be on the top or the bottom, 90 degrees between those bonds. Okay, now, this electron geometry gives rise to a couple other molecular geometries. So let's dig into that right now. So when I put a lone pair in this structure, so I take off a bond, I would have to take it off of the 120 degrees because lone pairs take up a little bit more space, causes more repulsion, so I'm going to take it right here. So where you see this empty stick, that means it's a lone pair. So this new shape, in the way you look at it, is if you put it on the ground where the lone pair sticks vertically on top, you'll see it to be a seesaw shape. The seesaw shape, looking at this angle, is a lot more visible. So again, seesaw. Imagine yourself sitting on both of these two atoms right here, a friend and yourself, and playing on the seesaw, okay? So this shape actually has two angles associated with it. There is an angle that is less than 90, and we can call it 87.5 because the lone pair causes a 2.5 degree squeeze on any of the angles around that, within the structure. So that's less than 90, which is 87.5 degrees. And then this lone pair also causes this angle to no longer be 120, but 117.5 degrees. Okay, so it causes the 2.5 degrees angle squeeze. Okay, so this shape is called seesaw. It's AB4E1. Now we get to another shape that arises from the electron geometry of a trigonal bipyramidal. The next one is where we're going to pull off a bonded atom at the same location or in the same plane as where you pulled off the other bond of this bond right here. So you're going to pull it off right here where the trigonal planar shape or plane is. And in doing so, now you have two lone pairs. And the shape of this structure looks exactly what the name of it is, which is T-shaped. The angle is no longer, it's not 90 like you think it is, but it's caused, these two lone pairs cause these angles to squeeze down just a little bit more. And the squeeze is going to be 100, and if you take 100, or sorry, not 100, so it's 87.5, so 2.5, so it's 85 degrees. So 85 degrees along this size angle right here, all the bonds, okay? So now we're gonna pull off a third one. Again, another shape that arises from the trigonal bipyramidal shape. In removing the third one, we're also gonna remove it off of the same trigonal planar plane. And in doing that, now you have a shape that causes equal repulsion from each of these lone pairs that are right on that plane. And thus, it won't move down because there's repulsion from those lone pairs. It won't move up because there's repulsion from those lone pairs. And so the shape is called linear, okay? And so the angle right here is 180 perfectly. So you've got to be careful. Lone pairs don't always suggest an exact angle squeeze of 2.5. It's only depending on where it's located in the structure. All right, so let's now move on to another expanded octet. The next expanded octet is a shape called a trigonal or octahedral. In the octahedral shape, you have 4 on a single plane. So 1, 2, 3, and 4. So now all the angles in this octahedron shape are 90 degrees, all 90 degrees, okay? So 90 degrees right here, 90 degrees within the square part of the planar shape there. They call this the equatorial plane versus the vertical plane, or the horizontal plane versus the vertical plane. So in the horizontal plane, you'll see 4 bonds, and it makes that square shape on the bottom there. But they're all, when you take diagonals of the perfect square, they're perpendicular, and that's why you see them as 90. And then, of course, this is obviously 90 as well, okay? Hopefully you lift it up. So again, octahedral, because this AB6 notation has 8 faces. 1, 2, 3, 4, and then another 4 from flipping it the other way. So again, octahedron. Now, when you start to look at other shapes that arise from this electron geometry, you really don't have a choice other than to say, I'll pick a side because they're all 90 degrees. I'll pick a side and remove that electron for that lone pair. So this is AB5, E1. So when you look at the shape for this, it is a square, it has a square base. So if you look at the square on the bottom, this is your square base. And it looks like a pyramid because it's got that apex on the pyramid, which is now, we call this square pyramidal. And the angles, no longer is it 90, it's 87.5 because that lone pair squeezes those angles by 2.5 degrees. Okay. Now we go to the next one where it's AB4, E2. In AB4, E2, you have to have another lone pair. So there's total of 2 lone pairs. And I have to take that lone pair off of this position because lone pairs do cause more repulsion, and the best location for removal is right here on the top. And so now what shape this is it's a square, so it makes a square, and it's on a flat plane, so we call this square planar. Very intuitive. Now, once again, even though the lone pairs they usually cause that 2.5 degree squeeze, but one is on top and the other one's going to be on the bottom, so whatever repulsion occurs from this top one will be balanced out with the repulsion from the bottom. And so all the angles are precisely 90 degrees all around. So now we go to the next one. So now it's AB3, E3. So I'm going to remove this, and when I remove this bond, now I have a shape called the T-shape. The T-shape will have repulsion of 2.5 because of this particular lone pair. And so when you move it down, you'll see that it's 87.5 degrees. And then, of course, the last one that rises from the octahedron shape is AB2, E4. And when that happens, it's all repelling along this horizontal plane right here, causing this angle to be 109, and the shape is 180, sorry. And so the shape is linear. I hope this helps. Please let me know and give me feedback on that, but replay it if you need to review your shapes from the VSEPR theory.